Good evening, and welcome to The Gentle Scientist. Tonight, we will drift together through the vastest story ever told, a journey across 13.8 billion years and 93 billion light-years of space, exploring the universe that cradles us all. Look up at the night sky on a clear evening, and you are seeing what humans have gazed upon for countless generations. Those distant points of light have guided travelers, inspired poets, and puzzled philosophers since our ancestors first learned to wonder. The stars are ancient companions, silent witnesses to all of human history, yet they are far stranger and more magnificent than our ancestors could have imagined. Each one is a nuclear furnace, burning with the same processes that forge the very atoms of your body. You are connected to them, quite literally made of their remnants, stardust gathered briefly into consciousness. Tonight, we will wander through cosmic history together, beginning with the universe's birth in the Big Bang, when everything burst into existence in a moment of unimaginable heat and light. If you enjoy these calming science journeys, feel free to like the video and subscribe to The Gentle Scientist, or take a moment to share a thought in the comments below. And now, there is nothing you need to do but listen, relax, and let curiosity carry you. You can close your eyes if you wish. You can let sleep come whenever it calls. Let's begin this quiet journey together, drifting through space and time, discovering the cosmos that is, in every sense, our home. In the beginning, there was everything and nothing all at once. About 13.8 billion years ago, the universe burst into existence from a state so impossibly hot and dense that our everyday words struggle to describe it. Imagine all of space, all of time, all of matter, compressed into a point smaller than the smallest thing you can picture. And then, in an instant that defies imagination, it began to expand. This was not an explosion in space, but an explosion of space itself. Space and time were born together in that first moment, unfurling like a flower, opening to the morning sun. Except there was no morning yet, no sun, no flowers. Only pure energy cascading outward, cooling as it went, beginning the long, gentle journey towards stars and planets, and eventually, somehow, toward us. The story of how we know this begins not with ancient myths or philosophical speculation, but with a quiet observation made nearly a century ago. In 1929, an astronomer named Edwin Hubble stood at his telescope and noticed something extraordinary. The galaxies scattered across the cosmos were not standing still. They were moving away from us, and the farther away they were, the faster they appeared to be receding. Hubble measured the light from distant galaxies and found it shifted toward the red end of the spectrum, stretched like a sound wave from a departing train. This redshift became a cosmic speedometer, revealing that galaxies rush away in all directions, as though the entire fabric of space itself is stretching. The pattern was elegant and precise, speed proportional to distance, a relationship now called Hubble's law. What does this mean? If everything is moving apart now, then long ago, everything must have been closer together. Run time backward in your mind, and you watch galaxies converge, space contract, the universe grow hotter and denser until you arrive at that singular beginning. The expansion we observe today is the echo of that primordial moment, still unfolding across billions of years. But expansion alone was not enough to convince every scientist. The universe needed more witnesses to testify to its fiery birth. And in 1965, those witnesses arrived in the form of a faint whisper from the ancient past. Two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting an annoying hiss in their antenna, a persistent static they could not eliminate. No matter where they pointed their instrument, the noise remained, uniform and unchanging. What they had stumbled upon was not interference, but a relic. It was the afterglow of the Big Bang itself, a bath of microwave radiation filling all of space. This cosmic microwave background, or CMB, is light that has been traveling for nearly 13.8 billion years, released when the universe was only 370,000 years old. Before that moment, the cosmos was too hot and dense for light to travel freely. Photons scattered endlessly off charged particles in a glowing fog. Then, as the universe expanded and cooled, atoms formed for the first time. Electrons settled into orbits around nuclei, and suddenly, space became transparent. Light broke free, streaming outward in all directions. That ancient light, stretched and cooled by billions of years of expansion, is what Penzias and Wilson heard as a hiss. It is what we now measure with exquisite precision as a faint glow at about 2.725 Kelvin, just a few degrees above absolute zero. The CMB is remarkably uniform, almost perfectly smooth across the entire sky. This uniformity tells us the early universe was extraordinarily homogeneous, a nearly perfect sea of energy and matter. Yet embedded in that smoothness are tiny ripples, fluctuations of only a few parts in 100,000. Satellites like COBE, WMAP, and Planck have mapped these ripples with stunning detail, revealing the seeds of everything that came after. Galaxies, clusters, the vast cosmic web. These fluctuations are like fingerprints left by quantum jitters in the newborn universe, stretched to cosmic scales by rapid expansion. Where the CMB is slightly warmer, matter was slightly denser. Where it is slightly cooler, matter was more sparse. Over hundreds of millions of years, gravity pulled matter toward the denser regions, slowly building the scaffolding upon which stars and galaxies would eventually form. The CMB is not the only relic of the Big Bang. In those first frantic minutes, when the universe was hotter than the core of any star, nuclear reactions forged the lightest elements. Protons and neutrons collided and fused, forming hydrogen, helium, and trace amounts of lithium. This process, called Big Bang nucleosynthesis, lasted only about 3 minutes, yet it determined the elemental composition of the universe for billions of years to come. When astronomers measure the abundance of these elements in ancient stars and primordial gas clouds, they find something astonishing. The ratios match precisely what the Big Bang model predicts. About 75% hydrogen, 25% helium, with just a whisper of lithium. This agreement is not a coincidence. It is a confirmation written in the chemistry of the cosmos that the universe began in a hot, dense state and has been cooling and expanding ever since. Yet even with expansion, the CMB and nucleosynthesis all aligning, cosmologists faced puzzles. Why is the universe so uniform on large scales? Why does space appear geometrically flat? And where did those tiny fluctuations in the CMB come from? The answer, proposed in the 1980s, is a period of extraordinary expansion called cosmic inflation. In the first fraction of a second after the Big Bang, perhaps as early as 10 to the minus 36 seconds, the universe underwent a rapid growth spurt. Space expanded exponentially, faster than the speed of light, doubling in size again and again in the blink of an eye. This inflationary epoch lasted only a minuscule instant, but it had profound consequences. Inflation smoothed out any initial wrinkles in space, explaining why the universe appears so uniform today. It stretched space flat, like pulling a balloon's surface taut until any curvature becomes imperceptible. And it took tiny quantum fluctuations, random jitters in the fabric of space-time, and amplified them to cosmic proportions, planting the seeds that would grow into galaxies. Evidence for inflation comes from multiple sources. The patterns in the CMB match predictions from inflationary models with remarkable precision. The large-scale structure of the universe, the way galaxies cluster and form filaments, also aligns with what inflation would produce. It is a theory that stitches together observations into a coherent narrative, though the exact mechanism driving inflation remains a mystery still quietly waiting to be unraveled. The Big Bang is not a single fact, but a tapestry woven from many threads of evidence. The expansion of space discovered by Hubble, the ancient glow of the CMB, the primordial abundance of elements, the inflationary solution to cosmic puzzles. Each thread strengthens the others, creating a picture of a universe that began in unimaginable heat and has been evolving, cooling, and complexifying ever since. To think that all of this, every star you see at night, every galaxy swirling in the depths of space, every atom in your body, traces back to that singular moment is both humbling and awe-inspiring. The Big Bang is not just a theory about the past. It is the foundation upon which the entire story of cosmic evolution rests. It is the opening chapter of the longest book ever written, a book still being penned across billions of light years. The universe is old, unfathomably, magnificently old. When we say it is about 13.7 to 13.8 billion years old, we are speaking of a span of time so vast that human lifetimes dissolve into it like raindrops in an ocean. To comprehend this age is to stand at the edge of a temporal abyss, peering back through billions upon billions of years to a beginning we can measure but barely imagine. How do we know this number? How can we claim to measure the age of everything with such confidence? The answer lies in multiple lines of evidence, each independently pointing to the same ancient date, like witnesses from different corners of existence, all telling the same story. We measure the expansion of the cosmos itself, watching how fast galaxies fly apart and calculating backward to when they were together. We study the oldest star clusters, those ancient cities of suns whose ages can be estimated from their stellar populations and the physics of how stars burn and fade. We examine radioactive elements, their decay rates ticking like atomic clocks buried in meteorites and ancient rocks, whispering secrets about the age of the solar system, and, by extension, the minimum age of the universe that contains it. All these methods converge on the same time frame. The The universe began its journey approximately 13.8 billion years ago, give or take 100 million years. In cosmic terms, that uncertainty is barely a margin at all. It is a testament to the precision of modern cosmology that we can speak of the universe's age with such confidence, measuring eons as carefully as a clockmaker measures seconds. But age is only half the story. The universe is not only ancient, it is vast. Staggeringly, incomprehensibly vast. When we speak of the observable universe, we mean the region of space from which light has had time to reach us since the beginning. This is not the entire universe, which may extend far beyond what we can see, perhaps infinitely. The observable universe is a bubble centered on Earth, defined by the speed of light and the finite age of the cosmos. Light travels fast, faster than anything else in nature, covering about 300,000 kilometers every single second. In 1 year, light crosses roughly 9.5 trillion kilometers, a distance we call a light year. It is a measure not of time, but of space, a yardstick for the cosmos. Given that the universe is 13.8 billion years old, you might expect the observable universe to stretch 13.8 billion light years in every direction, making it about 27.6 billion light years across. But the universe has a surprise waiting. The observable universe is actually about 93 billion light years in diameter. It extends roughly 46 billion light years from Earth in every direction. How can this be? How can we see light from regions farther away than the age of the universe would allow? The answer lies in the expansion of space itself. While light was traveling toward us from distant galaxies, space was expanding beneath it, stretching the distance between here and there. Imagine an ant walking across the surface of a balloon while someone inflates it. The ant moves forward, but the balloon's surface stretches, carrying the starting point farther away even as the ant marches on. Light does the same, crossing space even as space itself expands, lengthening the journey far beyond what a static universe would permit. This expansion means that galaxies we observe today, whose light left them billions of years ago, are now much farther away than they were when that light began its journey. The most distant, observable objects, whose light has been traveling for nearly the entire age of the universe, are now some 46 billion light years distant. They have been carried away by the expansion of space, riding the swelling fabric of the cosmos itself. To visualize this scale is nearly impossible. If you could somehow stand outside the observable universe and see it all at once, it would appear as an enormous sphere, 93 billion light years across, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. The Milky Way, our home galaxy, would be a single grain of sand on an infinite beach. Earth would be invisible, a mote lost in the immensity. This scale is not merely a curiosity. It is the stage upon which all known cosmic events unfold. Every supernova that has ever exploded, every black hole that has ever formed, every planet that has ever cooled into a cradle for life, all of it happens within this vast sphere. Beyond the observable horizon lies more universe, perhaps infinitely more, but it is forever hidden from us, its light not yet having had time to reach our eyes. The horizon itself is not static. It grows with time. As the universe ages, light from ever more distant regions finally completes its long journey to Earth, expanding our view of the cosmos. Every moment, new light arrives, carrying information from farther and farther away. Though the expansion of space means these regions are receding from us even as their ancient light reaches us. It is a strange dance, this interplay of light and expansion, where we see the past of a universe that has moved on. Galaxies, clusters, superclusters, and cosmic voids are spread across this immense volume, organized into a web-like structure of staggering complexity. Clusters of galaxies gather along filaments of dark matter, creating highways of light separated by vast empty regions. The observable universe is not a uniform sea, but a foam of structure, with matter clumped and clustered in patterns that echo the tiny fluctuations in the cosmic microwave background. Scientists measure the age and size of the universe using tools of breathtaking sophistication. The cosmic microwave background, that relic glow from the early universe, carries encoded within it information about the cosmos's age, geometry, and composition. Observations of type Aya supernovae, exploding stars that shine with predictable brightness, serve as cosmic distance markers, allowing astronomers to map the expansion history of the universe across billions of years. Galaxy redshift surveys measure how fast galaxies recede, tracing the stretching of space and inferring the timeline of expansion back to its origin. Each measurement refines our understanding, narrowing the uncertainties, building confidence in the grand narrative. The universe is 13.8 billion years old, vast beyond imagining, and filled with wonders we are only beginning to comprehend. To know this is to hold in your mind a number that encompasses all of history, not just human history, but the history of stars and galaxies, of light and matter, of time itself. When we speak of the universe's shape, we are not asking whether it resembles a sphere or a cube, but something far more subtle and profound. We are asking about the geometry of space itself, the fundamental curvature woven into the fabric of existence. This question matters deeply, for the shape of the universe influences how it expands, how light travels through it, and ultimately, what fate awaits everything within it. Imagine for a moment that you could step outside the universe and observe its geometry as a whole. What would you see? Would space curve back on itself like the surface of a sphere, where traveling far enough in one direction eventually brings you back to where you started? Would it curve outward like a saddle, stretching infinitely in all directions with negative curvature? Or would it be perfectly flat, extending forever in straight lines like an infinite plane? These three possibilities represent the fundamental geometries that cosmologists consider: positive curvature, negative curvature, and zero curvature. Each corresponds to a different fate for the cosmos and a different mathematical description of how distances and angles work on the largest scales. A positively curved universe, shaped like the surface of a sphere, would be finite in extent. Light traveling in a straight line would eventually return to its starting point, though the journey might take longer than the age of the universe. Such a universe would be closed, its expansion eventually halting and reversing, pulling everything back together in a cosmic collapse, sometimes called the Big Crunch. A negatively curved universe, shaped like a saddle or a hyperbolic surface, would be infinite and open. Its expansion would continue forever, accelerating outward with no possibility of reversal. In this geometry, parallel lines diverge, and the angles in triangles sum to less than 180 degrees. It is a strange, counterintuitive space, difficult to visualize, but mathematically elegant. A flat universe with zero curvature sits precisely on the boundary between these two extremes. It extends infinitely in all directions, yet its expansion follows a delicate balance. In a flat universe without dark energy, expansion would slow over time but never quite stop, asymptotically approaching zero velocity. With dark energy, as our universe appears to have, a flat geometry still permits eternal expansion, driven by this mysterious repulsive force. For decades, determining which of these geometries describes our universe was one of cosmology's great quests. The answer lay hidden in subtle measurements, in the precise angles and distances of cosmic structures, in the patterns imprinted on the cosmic microwave background, and in the distribution of galaxies across the sky. The cosmic microwave background became the key to unlocking this mystery. This ancient light, released when the universe was only 370,000 years old, carries within it patterns that depend sensitively on the geometry of space. Imagine sound waves rippling through the hot plasma of the early universe, creating regions of slightly higher and lower density. When the universe cooled enough for atoms to form, these density variations froze into place, imprinted as temperature fluctuations in the CMB. The size of these fluctuations, the angular scale at which they appear on the sky, depends directly on the curvature of space. In a flat universe, the largest fluctuations appear at about 1 degree across. In a positively curved universe, they would appear larger, magnified by the focusing effect of curved space. In a negatively curved universe, they would appear smaller, diminished by the diverging geometry. Satellites like WMAP and Planck mapped the cosmic microwave background with exquisite precision, measuring the temperature of the sky at millions of points. They charted the fluctuations, analyzed their patterns, and compared them to theoretical predictions. The results were stunning. The angular size of the largest fluctuations matched almost exactly the predictions for a flat universe. Space, on the largest scales, appears to be geometrically flat, supporting evidence arrived from other observations. Baryon acoustic oscillations, subtle patterns in the distribution of galaxies, also reflect the geometry of space. These oscillations are like fossilized sound waves, frozen into the cosmic web when the universe was young. Measuring their size and distribution provides another independent test of curvature, and once again, the answer pointed to flatness. Large-scale structure surveys, mapping millions of galaxies across vast volumes of space, revealed clustering patterns consistent with flat geometry. The way galaxies organize themselves into filaments, clusters, and voids follows expectations derived from a flat universe, seeded with tiny density fluctuations in the early cosmos. Precision cosmology, combining all these measurements, has determined that the universe is flat to within a tiny margin of error, less than 0.5%. If there is any curvature at all, it is so slight that we cannot yet detect it. For all practical purposes, the universe we inhabit is geometrically flat, a vast infinite expanse where the familiar rules of Euclidean geometry hold true on the largest scales. This flatness is remarkable because it requires extraordinary fine-tuning. The density of matter and energy in the universe must be almost exactly at a critical value, a precise balance between too much and too little. If the density were even slightly higher, the universe would have positive curvature and would have collapsed long ago. If it were slightly lower, space would have negative curvature and would have expanded too rapidly for galaxies to form. This delicate balance is quantified by a parameter called omega, the ratio of the universe's actual density to the critical density needed for flatness. Observations show that omega is extraordinarily close to 1, meaning the universe sits right at the knife's edge between open and closed geometries. Why should this be? What mechanism could produce such precise flatness? The answer, cosmologists believe, lies in cosmic inflation, that brief but explosive period of expansion in the first fraction of a second after the Big Bang. Inflation stretched space so rapidly that any initial curvature was smoothed out, much like inflating a balloon makes its surface appear flatter and flatter. Even if the universe started with significant curvature, inflation would have diluted it to imperceptible levels, driving the geometry toward perfect flatness. Inflation thus predicts a flat universe, and observations confirm this prediction. The agreement between theory and measurement is one of modern cosmology's great triumphs, a quiet validation that our understanding of the cosmos's earliest moments is fundamentally sound. The implications of a flat universe extend to its ultimate fate. In a flat geometry dominated by dark energy, as our universe appears to be, expansion will continue forever. Galaxies will drift apart, stars will burn out, and eventually the cosmos will fade into a cold, dark expanse. Yet this fate unfolds over timescales so vast they make the current age of the universe seem like a fleeting moment. Trillions upon trillions of years separate us from that distant twilight. To live in a flat universe is to inhabit a cosmos balanced on the edge of infinity. It is a space that extends forever in all directions, yet remains comprehensible, governed by the same geometric principles that describe triangles and circles in school textbooks. The shape of all space turns out to be the simplest possible shape, a testament perhaps to an underlying elegance in nature's design. This flatness is not merely an abstract curiosity. It is the silent backdrop to everything that happens in the cosmos. Every photon of light travels in straight lines through this flat space. Every gravitational interaction unfolds according to equations that assume flatness on large scales. The cosmic web of galaxies, the clustering of matter, the expansion of space itself, all reflect this fundamental geometry. As you consider this, imagine standing at the center of an infinite plane stretching away in all directions, knowing that you are not truly at the center because in an infinite flat space, every point is the center. The universe has no edge, no boundary, no privileged location. It is flat, vast, and everywhere the same in its deepest structure. This is the stage upon which the cosmic drama unfolds, a quiet foundation supporting all the brilliance and beauty scattered across the heavens. There is more to the universe than meets the eye. In fact, most of the universe is invisible, hidden in a form of matter so elusive it passes through walls, through planets, through your body at this very moment without leaving a trace. This mysterious substance is called dark matter, and it makes up roughly 80% of all the matter in the cosmos. Everything we can see, stars blazing in the night, glowing nebulae, swirling galaxies, all of it combined accounts for only a fraction of what truly exists. The rest dwells in shadow, detectable only by its gravitational whisper. The story of dark matter begins not with what we can see, but with what we cannot explain. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a vast congregation of galaxies bound together by gravity. He measured how fast these galaxies were moving, expecting their velocities to match the visible mass he could observe. But the galaxies were moving far too quickly. At those speeds, they should have flown apart long ago, scattering into the cosmic void. Yet there they remained, held together by some unseen hand. Zwicky calculated that the cluster must contain far more mass than what's shown in starlight. He called this missing mass Dunkel Materie, dark matter. For decades, his idea languished on the edges of astronomy, a curious anomaly that few took seriously. But in the 1970s, another astronomer would provide evidence so compelling that dark matter could no longer be ignored. Vera Rubin turned her telescope toward spiral galaxies, measuring how fast stars orbit at various distances from the galactic center. In a typical solar system, planets farther from the sun move more slowly, following the predictable laws of gravity and orbital mechanics. Rubin expected galaxies to behave the same way, with stars in the outer regions moving more slowly than those near the center where most visible mass resides. What she found instead was astonishing. Stars at the edges of galaxies were moving just as fast as those closer in, their velocities remaining nearly constant no matter how far out she measured. The rotation curves were flat, impossibly flat, defying everything known about gravity, unless there was something else present, something invisible providing additional gravitational pull. The only explanation was that galaxies are embedded in vast halos of dark matter, extending far beyond the visible disk of stars, their mass dominating the gravitational landscape. Dark matter does not emit light. It does not absorb light. It does not reflect light. It is invisible to every form of electromagnetic radiation we have ever devised. We cannot see it with our eyes, cannot photograph it with telescopes, cannot detect it with radio dishes or X-ray observatories. It interacts with ordinary matter only through gravity, bending space around it, pulling on stars and galaxies, shaping the very structure of the cosmos. One of the most dramatic demonstrations of dark matter's existence comes from gravitational lensing. According to Einstein's theory of general relativity, massive objects bend the fabric of space-time, and light traveling through this curved space follows the bends. When light from distant galaxies passes through a cluster of galaxies in the foreground, the cluster's gravity acts like a cosmic magnifying glass, distorting and amplifying the background light into arcs and rings. Astronomers can map the strength of this lensing effect to determine where the mass is located. Time and again, they find that the lensing is far stronger than the visible matter alone could produce. The gravitational distortions trace enormous halos of invisible mass surrounding galaxy clusters, confirming that dark matter is not just present, but dominant, outweighing ordinary matter by a factor of 5 to 1. Perhaps the most compelling evidence comes from the Bullet Cluster, where two galaxy clusters collided and passed through each other. The hot gas between galaxies, which makes up most of the ordinary matter, slowed down during the collision, interacting and radiating energy. But the dark matter, interacting only through gravity, passed through unimpeded. Observations show the bulk of the mass, revealed through gravitational lensing, separated from the visible gas, providing a clear spatial distinction between dark and ordinary matter. It is as though two invisible ghosts passed through each other, while their luminous cloaks tangled and fell behind. Dark matter is not distributed randomly across the universe. It forms the cosmic web, an intricate scaffolding of filaments and halos that underlies all visible structure. Imagine a vast, three-dimensional tapestry woven from invisible threads, stretching across hundreds of millions of light years. Galaxy clusters sit at the nodes where filaments intersect, like cities along highways. Between the filaments lie enormous voids, regions nearly empty of both dark and ordinary matter, silent and dark. This cosmic web emerged gradually from the tiny density fluctuations imprinted in the early universe. Regions slightly denser than average had slightly stronger gravity, pulling in more matter over time. Dark matter, being far more abundant than ordinary matter, dominated this process. Its gravity drew ordinary matter into the same regions, allowing gas to cool and collapse, forming stars and galaxies within the dark matter halos. Without dark matter, the universe would look entirely different. Galaxies would be small and fragile, unable to hold themselves together. The cosmic web would not exist. Structure formation would have unfolded far too slowly to produce the rich tapestry of galaxies we observe today. Dark matter acts as gravitational glue, binding the cosmos together, providing the framework upon which all visible structure hangs. Evidence for dark matter comes from multiple independent sources, each one reinforcing the others. The rotation curves of galaxies, the motion of galaxy clusters, gravitational lensing, the cosmic microwave background, and large-scale structure simulations all point to the same conclusion. The universe is dominated by an invisible form of matter we have yet to fully understand. What is dark matter made of? This remains one of the deepest mysteries in science. It cannot be ordinary matter, protons, neutrons, electrons, because the abundance of light elements forged in the Big Bang constrains how much ordinary matter can exist. Dark matter must be something else, a type of particle that has never been seen in laboratories, perhaps a relic from the earliest moments of the universe. One leading candidate is the WIMP, a weakly interacting massive particle, predicted by theories extending the standard model of particle physics. WIMPs would interact only through gravity and the weak nuclear force, making them incredibly difficult to detect. Experiments buried deep underground, shielded from cosmic rays, search for the rare occasions when a WIMP might collide with an atomic nucleus. So far, these experiments have found nothing, setting ever stricter limits on what dark matter could be. Another candidate is the action, a hypothetical particle originally proposed to solve a problem in quantum chromodynamics. Axions would be far lighter than WIMPs, more like ghostly waves than particles, but they could still account for dark matter if they exist in vast numbers. Experiments are underway to search for axions, attempting to convert them into detectable photons using strong magnetic fields. Despite decades of searching, dark matter particles have not been directly detected. Yet the gravitational evidence for their existence is overwhelming. They are there, woven into the fabric of the cosmos, invisible but undeniable. Every galaxy rotation curve, every gravitational lens, every simulation of cosmic structure formation confirms their presence. For most of the 20th century, astronomers believed they understood the universe's fate. Gravity, they thought, must be slowing the expansion that began with the Big Bang. Like a ball thrown upward, the cosmos should gradually decelerate, its outward motion restrained by the gravitational pull of all the matter within it. The only question was whether there was enough mass to eventually halt and reverse the expansion, or whether the universe would expand forever, slowing but never quite stopping. Then, in the late 1990s, two teams of astronomers made a discovery that would overturn this comfortable picture and plunge cosmology into a new era of mystery. They were studying Typea supernovae, exploding stars that shine with such predictable brightness. They serve as cosmic distance markers, standard candles scattered across the universe. By measuring how bright these supernovae appear and comparing that to how bright they should be, astronomers can calculate their distance with remarkable precision. The teams expected to find that distant supernovae, whose light left them billions of years ago, would appear brighter than expected if the expansion of the universe had been slowing over time. Instead, they found the opposite. The supernovae were dimmer, fainter than they should be, meaning they were farther away than anticipated. The universe's expansion was not slowing down at all, it was speeding up. This was not a small discrepancy. The acceleration was clear, undeniable, present in supernova after supernova at varying distances. Something was pushing the universe apart, driving galaxies away from each other at an ever-increasing rate. Gravity, the force that should be pulling everything together, was being overwhelmed by something else, something with the opposite effect. The discoverers called it dark energy, and its existence would earn them the Nobel Prize. Dark energy is perhaps the most profound mystery in all of science. It is not matter. It does not clump or cluster. It does not emit light or interact with ordinary particles in any detectable way. Instead, it behaves like a property of space itself, a kind of repulsive gravity or negative pressure that grows stronger as the universe expands. The more space there is, the more dark energy there is, and the faster the expansion accelerates. Einstein had encountered something similar decades earlier, when he first applied his equations of general relativity to the universe as a whole. He found that space could not remain static. It would either expand or contract. At the time, the prevailing belief was that the universe was eternal and unchanging. So Einstein added a term to his equations, the cosmological constant, to counteract gravity and hold the universe still. When Hubble discovered that the universe was indeed expanding, Einstein famously called the cosmological constant his greatest blunder and removed it from his equations. Now, nearly a century later, the cosmological constant has returned, no longer as a mistake, but as a description of dark energy. In modern cosmology, it appears as the Greek letter lambda in the equations, representing a constant energy density filling all of space. This lambda cold dark matter model, or LCDM, has become the standard framework for understanding the cosmos. According to this model, dark energy makes up roughly 70% of the universe's total energy density, with dark matter accounting for about 25% and ordinary matter just 5%. We are made of the rarest substance in the universe. The evidence for dark energy extends beyond supernovae. Measurements of the cosmic microwave background reveal a universe that is geometrically flat. But the density of matter alone is not enough to achieve this flatness. Dark energy provides the additional energy density needed to balance the cosmic scales. Large-scale surveys mapping the distribution of galaxies across billions of light years show clustering patterns consistent with a universe where dark energy dominates the recent expansion history. Baryon acoustic oscillations, subtle patterns imprinted in the distribution of galaxies, serve as another cosmic ruler, measuring distances and the expansion rate at different epochs. These measurements confirm that the universe's expansion was decelerating in the early eras when matter dominated, but began accelerating a few billion years ago as dark energy took over. Yet for all this evidence, we do not truly understand what dark energy is. The simplest explanation is that it is a cosmological constant, an unchanging property of the vacuum of space itself. Quantum field theory suggests that empty space is not truly empty, but seethes with virtual particles popping in and out of existence, each contributing a tiny amount of energy. The problem is that when physicists calculate the expected energy of the vacuum, they get a number that is 10 to the 120th times larger than the observed dark energy density. It is one of the worst predictions in the history of science, a discrepancy so enormous it suggests we are missing something fundamental. Some cosmologists have proposed that dark energy is not constant, but changes over time, a dynamic field that evolves as the universe ages. This idea, sometimes called quintessence, would mean dark energy had different strengths in the past and may have different strengths in the future. Recent observations from the Dark Energy Spectroscopic Instrument, or DESI, have hinted at intriguing possibilities along these lines. DSI maps millions of galaxies and quasars across vast stretches of cosmic history, measuring how the expansion rate has changed over billions of years. Early results suggest that dark energy may not be perfectly constant. There are indications, still preliminary and requiring further confirmation, that dark energy's strength was greater in the past and has been gradually weakening over time. If true, this would be revolutionary, suggesting dark energy is not Einstein's cosmological constant, but something more complex, a field with its own dynamics and evolution. The implications are profound. If dark energy is weakening, the universe's fate could be different from what we expect. In a cosmos dominated by a constant dark energy, the expansion accelerates forever. Galaxies recede beyond each other's horizons, stars eventually burn out, and the universe fades into a cold, dark, infinitely dispersed state sometimes called the Big Freeze or heat death. But if dark energy is changing, other possibilities open up. It could strengthen, tearing galaxies, stir and eventually atoms apart in a big rip. Or it could weaken further and even reverse, though current observations give no hint of this. Dark energy also raises deep questions about the nature of space and time. If empty space carries energy, what does that mean for the vacuum? Is space a substance with properties? Or is it truly nothing? Quantum mechanics and general relativity, our two most successful theories, give conflicting answers. Reconciling them in a theory of quantum gravity might finally explain dark energy. But such a theory remains elusive, a distant goal toward which physicists are still working. The accelerating expansion discovered through supernovae has transformed our understanding of the cosmos. We live in a universe not winding down into a gravitational collapse, nor coasting to a gradual halt, but one rushing outward ever faster, driven by a mysterious force that permeates every cubic centimeter of space. This realization came as a shock, a reminder that the universe is stranger and more wondrous than our theories had imagined. To picture dark energy, imagine space itself as elastic, capable of stretching, and embedded with an intrinsic tension that pushes outward. As the universe expands, more space comes into existence, bringing with it more dark energy. This creates a feedback loop. More space means more dark energy, which drives faster expansion, creating even more space. It is a runaway process. Gentle now, but relentless, ensuring that the cosmos will grow larger and emptier as eons pass. For now, galaxies remain bound together by gravity, and clusters of galaxies form stable systems. Dark energy's influence is strongest on the largest scales, pushing apart structures that are not tightly bound. But as billions of years pass, dark energy's grip will tighten. Distant galaxies will accelerate away, their light red-shifted beyond visibility. The observable universe will shrink, not because space is contracting, but because expansion carries distant regions away faster than light can travel. Future observers, if any exist, might look out into a universe containing only their local cluster, isolated in an ever-expanding void, with no evidence of the broader cosmos we see today. This fate unfolds over timescales almost beyond comprehension. Trillions of years from now, long after the sun has died, long after the Milky Way has merged with Andromeda, long after the last stars have flickered out. Yet even contemplating such distant futures brings a strange comfort. The universe is not ending soon. It has time, vast quantities of time, to continue its slow dance of creation and dissolution. In the beginning, after the Big Bang's first fiery moments had passed, the universe was a vast ocean of gas. Hydrogen and helium drifted through the darkness, thinly spread across expanding space. With no stars to illuminate them, no galaxies to give them form. For hundreds of millions of years, this cosmic fog persisted in what astronomers call the Dark Ages, a time when the universe held only potential, waiting patiently for gravity to weave the first threads of light. But even in this darkness, seeds were already planted. Tiny fluctuations in density, quantum ripples stretched to cosmic scales by inflation, created regions where gas was slightly denser than average. These subtle variations, invisible at first, would become the architects of all structure. Gravity, patient and inexorable, began pulling gas toward these denser regions. Slowly, imperceptibly at first, matter began to gather. Dark matter played a crucial role in this gathering. Its gravity shaped invisible halos, vast cocoons of mass that drew ordinary gas inward like moths to a flame. The gas fell into these dark matter wells, pooling in their centers, heating as it compressed. Yet dark matter itself remained aloof, a silent scaffolding that shaped everything but touched nothing, interacting only through the gentle pull of gravity. As gas clouds grew denser, they began to cool, radiating away heat into the void. Cooling allowed them to collapse further, fragmenting into smaller clumps under their own weight. Within these collapsing clouds, temperature and pressure rose. Atoms collided more frequently, their motion more violent. In the densest regions, something extraordinary began to happen. The first stars were born perhaps 100 to 200 million years after the Big Bang. They were nothing like the Sun. These population 3 stars, as astronomers call them, formed from pristine gas containing only hydrogen and helium, untainted by heavier elements. Without metals to help the gas cool and fragment, these first stars grew enormous, hundreds of times more massive than the Sun, blazing with fierce blue light. Their lives were brief but glorious. Massive stars burn hot and fast, consuming their nuclear fuel in mere millions of years compared to the billions that smaller stars enjoy. They fused hydrogen into helium, helium into carbon and oxygen, building heavier elements in their cores through the elegant alchemy of nuclear fusion. When their fuel was exhausted, they exploded as supernovae, scattering newly forged elements into space and lighting the cosmos with brilliant flashes that marked the end of the Dark Ages. These explosions seeded the universe with the first heavy elements, enriching the surrounding gas. Subsequent generations of stars would form from this enriched material, inheriting carbon, oxygen, nitrogen, and iron. The building blocks not just of stars, but of planets and eventually of life itself. Star formation did not happen in isolation. As gas collected in dark matter halos, it formed rotating disks and clumps that would become the first galaxies. These early galaxies were small, irregular collections of stars, nothing like the grand spirals we see today. They contained perhaps millions of stars rather than hundreds of billions, scattered across regions only a few thousand light-years across. But these small galaxies were just the beginning. Gravity continued its work, pulling galaxies toward each other, causing them to merge and grow. Galaxy formation is a hierarchical process, a cosmic version of building with blocks, where small structures combine to form larger ones. Two small galaxies collide and merge, their stars mingling, their gas clouds compressing and triggering new bursts of star formation. The merged galaxy then collides with another, growing larger still. Over billions of years, this process built the great galaxies we observe today. The Hubble Space Telescope, and later the James Webb Space Telescope, have peered deep into the universe, looking back in time to when galaxies were young. They have found tiny, irregular systems actively forming stars at prodigious rates. Their light reddened by the expansion of space, stretched across billions of years of cosmic history. These observations reveal galaxies in various stages of assembly, from small clumps barely distinguishable from the cosmic fog, to mature spirals and ellipticals resembling those in our local universe. The diversity is stunning. Some galaxies appear as disks with graceful spiral arms, regions where gas and dust trace elegant curves, punctuated by bright knots of star formation. Others are elliptical, smooth, and featureless, their stars moving in random orbits with little organized rotation, shaped by violent mergers that scrambled their structure. The Milky Way itself formed through this process. It began as a small protogalaxy, one among many in the early universe. Over billions of years, it grew by accreting smaller galaxies, consuming them and incorporating their stars. Even today, this process continues. The Milky Way is slowly devouring several dwarf galaxies that orbit it, streams of stars marking the paths of these smaller systems as they are torn apart by tidal forces. Within galaxies, star formation follows patterns dictated by the availability of cold, dense gas. Giant molecular clouds, vast reservoirs of gas and dust, serve as stellar nurseries. These clouds are cold, only tens of degrees above absolute zero, allowing gravity to compress them without the resistance of thermal pressure. Within these clouds, denser cores collapse, each one becoming a protostar. A protostar begins as a dim, red object, still gathering mass from the surrounding cloud. It spins, flattening into a disk as angular momentum spreads material outward. Jets of gas stream from the poles, launched by magnetic fields, twisted by the spinning disk. This is a turbulent, chaotic phase, the birth pangs of a new sun. As the protostar grows, its core becomes denser and hotter. Pressure and temperature rise until, finally, a threshold is crossed. Hydrogen nuclei begin to fuse into helium, releasing tremendous energy. Nuclear fusion ignites, and a star is truly born. The energy radiating outward pushes back against the collapsing gas, establishing a balance called hydrostatic equilibrium. The star settles onto the main sequence, beginning the long, stable phase of its life. Star formation can be triggered by various events. When galaxies collide, their gas clouds compress and shock, sparking intense bursts of star formation called starbursts. Supernova explosions send shockwaves through nearby molecular clouds, compressing them and triggering new stars to form. Even the spiral arms of disk galaxies act as sites of star formation, their density waves compressing gas as it flows through them. Yet star formation is also regulated. Supernova explosions and powerful stellar winds can blow gas out of galaxies, removing the raw material needed to form new stars. Supermassive black holes lurking in galactic centers can heat surrounding gas with jets and radiation, preventing it from cooling and collapsing. This feedback balances star formation, preventing galaxies from converting all their gas into stars too quickly. Over cosmic time, the rate of star formation in the universe has declined. The peak occurred roughly 10 billion years ago, when galaxies were young and gas-rich. Since then, much of the available gas has been consumed or expelled, and the universe's expansion has made it harder for new gas to fall into galaxies. Today, star formation continues, but at a more sedate pace, a gentle twilight compared to the vigorous youth of the cosmos. Galaxies themselves are organized into larger structures. They gather in clusters, bound together by gravity, containing hundreds or thousands of galaxies in relatively small volumes. Clusters, in turn, line up along filaments of the cosmic web, vast highways of galaxies stretching across hundreds of millions of light years. Between the filaments lie voids, enormous empty regions where few galaxies exist, silent and dark. This cosmic web is not random, but reflects the initial distribution of dark matter and the tiny density fluctuations in the early universe. Computer simulations, starting from these initial conditions and evolving forward through billions of years, reproduce the observed structure with remarkable accuracy. The simulations show dark matter forming filaments first, with ordinary matter flowing along these channels, collecting at intersections where galaxies and clusters form. The diversity of galaxies we observe today reflects billions of years of cosmic history. Each galaxy carries a story written in its stars, its shape, its motion. Spiral galaxies speak of gentle evolution, gas-rich disks, forming stars in elegant patterns. Elliptical galaxies whisper of violent mergers that stirred their stars into smooth, featureless distributions. Irregular galaxies hint at ongoing disruption, tidal interactions distorting their forms. To look at a galaxy is to see a city of stars, each one a sun with its own potential for planets, perhaps life. Our Milky Way alone contains hundreds of billions of stars, and the observable universe holds hundreds of billions of galaxies. The numbers become almost meaningless, yet each galaxy is unique, each star a nuclear furnace blazing in the dark. Every star has a story, a journey that begins in darkness and ends in transformation. Stars are not eternal, though they may seem so to our brief human eyes. They are born, they live, and they die, each stage unfolding according to the elegant laws of physics, each star's fate written in the mass it gathered at birth. To understand stars is to witness some of the most profound cycles in nature, processes that create the very elements of which we are made. A star, begins its life in a nebula, a vast cloud of gas and dust drifting through the galaxy. These stellar nurseries are cold and dark, their material spread so thinly that they are almost transparent. Yet within them, gravity is always at work, seeking denser regions, pulling matter together grain by grain. When a region becomes dense enough, perhaps triggered by a passing shockwave from a nearby supernova or the collision of clouds, the collapse begins. As gas falls inward, it heats up, converting gravitational potential energy into thermal energy. The cloud fragments into smaller pieces, each one collapsing independently, each destined to become a star, or perhaps a companion in a binary system. At the center of each collapsing fragment, a protostar forms, a hot, glowing core surrounded by a swirling disk of material, still falling inward. This protostar phase is turbulent and beautiful. The young star has not yet ignited nuclear fusion, but it shines with the heat of gravitational contraction. It launches powerful jets from its poles, twin beams of gas, shooting outward at tremendous speeds, driven by magnetic fields tangled in the spinning disk. These jets carve through the surrounding nebula, creating bow shocks and glowing regions where they slam into the ambient gas. For hundreds of thousands to millions of years, the protostar continues to grow, accreting material from its disk. Its core grows denser and hotter. Temperature and pressure climb steadily upward. Then, when the core reaches about 10 million degrees Kelvin, something miraculous happens. Hydrogen nuclei, protons stripped of their electrons, begin to collide with enough energy to overcome their mutual electrical repulsion. They fuse together, forming helium and releasing tremendous energy in the process. Nuclear fusion has ignited. A star is born. The energy released by fusion radiates outward, creating pressure that pushes against the inward pull of gravity. An equilibrium is established, a delicate balance between the crushing weight of the star's own mass and the outward pressure of the energy being generated in its core. This balance defines the main sequence, the long, stable phase during which stars spend the majority of their lives. The Sun, our own star, has been on the main sequence for about 4.6 billion years and will remain there for another 5 billion or so. During all this time, it steadily converts hydrogen into helium in its core, shining with a nearly constant brightness, providing the stable energy that has allowed life to flourish on Earth. This stability is not unique to the Sun. All main sequence stars achieve this balance, though the details depend critically on mass. Mass is destiny for a star. A star's mass determines how hot its core burns, how quickly it consumes its fuel, and ultimately, how it will die. Massive stars, those many times the mass of the Sun, burn brilliantly but briefly. Their immense gravity compresses their cores to tremendous temperatures, accelerating fusion reactions to a furious pace. A star, 100 times the Sun's mass, might live only a few million years, a cosmic eye blink compared to the Sun's 10 billion year lifespan. Smaller stars, those less massive than the Sun, burn their fuel slowly and frugally. A red dwarf, only a tenth the Sun's mass, can shine for trillions of years, longer than the current age of the universe. These dim, cool stars are the most common in the galaxy, yet they are so faint that not a single one is visible to the naked eye from Earth. They will outlive nearly every other star, patiently burning hydrogen long after giants have exploded and the sun itself has faded. But eventually, even the most frugal star exhausts the hydrogen in its core. What happens next depends, again, on mass. For stars like the Sun, the end of main sequence life marks the beginning of profound changes. With no hydrogen left to fuse in the core, fusion ceases, and the core contracts under gravity. This contraction heats the surrounding layers, igniting hydrogen fusion in a shell around the now inert helium core. The energy from this shell burning causes the outer layers of the star to expand dramatically. The star swells into a red giant, growing hundreds of times its original size. Its surface cools, shifting from yellow to red, yet it becomes far more luminous because of its enormous size. The Sun, in about 5 billion years, will undergo this transformation. It will expand to engulf Mercury, perhaps Venus, possibly even reaching Earth's orbit, though by then, our planet will likely be a scorched, lifeless husk. In the core of the red giant, helium accumulates, growing denser and hotter as the overlying layers press down. When the core reaches about 100 million degrees, helium itself begins to fuse, combining 3 helium nuclei into a single carbon nucleus in a process called the triple alpha reaction. This helium fusion is briefer than hydrogen burning, lasting only a few 100 million years for a sun-like star. As helium runs low, the core contracts again, and if the star is massive enough, fusion progresses to heavier elements. Carbon fuses into oxygen into neon, and magnesium, each stage requiring higher temperatures and lasting for shorter periods. In the most massive stars, this process continues through silicon all the way to iron. Iron is where fusion stops. Iron nuclei are so tightly bound that fusing them consumes energy rather than releasing it. When a massive star's core turns to iron, it has reached the end of the line. For stars like the Sun, the end comes more gently. Unable to ignite carbon fusion, the core contracts into a dense, hot ember, while the outer layers drift away into space. These layers form a planetary nebula, not a planet at all, but a glowing shell of gas expanding outward, illuminated by ultraviolet light from the hot core left behind. The nebula's beauty is fleeting, dissipating into the interstellar medium over tens of thousands of years, recycling material that will someday form new stars. The core that remains is a white dwarf, an object roughly the size of Earth, but containing a significant fraction of the Sun's mass. It is incredibly dense. A teaspoon of white dwarf material would weigh as much as an elephant. The white dwarf shines not from fusion, which has ceased forever, but from residual heat, slowly cooling over billions of years until it fades into a cold, dark cinder, a black dwarf, though the universe is not yet old enough for any black dwarfs to have formed. Massive stars die more dramatically. When fusion ceases in their iron cores, disaster follows swiftly. With no energy generation to support the core against gravity, it collapses catastrophically in less than a second. The collapse is so violent that electrons are crushed into protons, forming neutrons and releasing vast numbers of neutrinos. The core rebounds, sending a shockwave outward that tears through the star's outer layers. The star explodes as a supernova, briefly outshining an entire galaxy. In those few seconds of cataclysm, more energy is released than the star emitted during its entire life. The explosion is also a cosmic forge. The intense heat and pressure create elements heavier than iron, gold, platinum, uranium, through rapid neutron capture. These elements, impossible to create in normal stellar fusion, are scattered into space along with all the lighter elements built up over the star's life. Supernovae are not just deaths, but births. They enrich the interstellar medium with heavy elements, seeding future generations of stars and planets. They also trigger star formation, their shock waves compressing nearby gas clouds and initiating collapse. The explosion that ends one star's life can spark the birth of hundreds of others. What remains after a supernova depends, once more, on mass. If the core is between about 1.4 and 3 solar masses, it becomes a neutron star, an object so dense that protons and electrons have merged into neutrons. A neutron star might be only 20 kilometers across, yet it contains more mass than the Sun. A sugar cube of neutron star material would weigh as much as all of humanity combined. Neutron stars often spin rapidly, sometimes hundreds of times per second, and if their magnetic fields are aligned properly, they emit beams of radiation that sweep across space like lighthouse beams. These are pulsars, discovered in 1967, and initially so regular in their pulses that astronomers briefly wondered if they were signals from extraterrestrial civilizations. Instead, they are nature's most precise clocks, the spinning remnants of dead stars. If the core exceeds about 3 solar masses, even neutron degeneracy pressure cannot resist gravity's crush. The core collapses beyond the neutron star stage, contracting past any known stopping point, forming a region of space where gravity is so intense that not even light can escape. A black hole is born, a tear in the fabric of space-time, a boundary beyond which nothing returns. These stellar remnants, white dwarfs, neutron stars, black holes, are the universe's memory, silent monuments to stars that once shone. They are also endpoints, objects that will persist essentially unchanged for timescales almost beyond imagination. White dwarfs will cool for trillions of years. Neutron stars and black holes, barring rare interactions, will endure far longer, perhaps until the universe itself ends, if it ever does. The life cycle of stars is fundamentally a story of transformation. Stars take the simplest elements, hydrogen and helium, and through fusion, convert them into the entire periodic table. Carbon, nitrogen, oxygen, the elements of life, are all manufactured in stellar cores and scattered by stellar winds and supernovae. The cycle continues, endless and patient. Dead stars enrich clouds. Clouds collapse to form new stars. Those stars eventually die and return their material to space. It is a cosmic recycling program, operating on timescales of millions and billions of years, creating complexity and beauty from from simple beginnings. Each star's journey is unique, yet all follow the same underlying principles: the elegant interplay of gravity, pressure, and nuclear physics. The cosmos is a garden where stars bloom and fade, each one contributing to the richness of the whole, each one a temporary brilliance in the long, gentle unfolding of cosmic time. Time flows differently in the cosmos than it does in our lives. We measure our days in heartbeats and sunrises, our years in seasons and birthdays, our lifetimes in memories accumulated and relationships formed. But the universe operates on scales so vast that our entire civilization, from its first stirrings to its possible distant end, occupies barely a flicker in the cosmic day. To understand the universe is to recalibrate our sense of time, to step outside the human experience and glimpse the deeper rhythms that pulse through space itself. At the heart of cosmic time lies a fundamental speed limit, a boundary written into the structure of reality. Nothing can travel faster than light. This is not merely a practical limitation, like the top speed of a car, but a consequence of how space and time are woven together. Light moves at approximately 300,000 kilometers per second, fast enough to circle the Earth 7.5 times in a single second. Yet this speed, while extraordinary by human standards, is finite. And that finitude has profound implications. The speed of light governs how quickly information can travel across the universe. When we look at the moon, we see it not as it is now, but as it was 1.3 seconds ago. The time it takes light to cross the space between Earth and Moon. The sun we see is 8 minutes in the past. The nearest star beyond the sun, Proxima Centauri, appears as it was 4 years ago. The Andromeda Galaxy, our nearest large galactic neighbor, shows us its light from 2.5 million years ago, when our ancestors were learning to use stone tools. This creates a peculiar feature of astronomical observation. We do not see the universe as it is, but as it was. The deeper we look into space, the further back in time we peer. The most distant galaxies, their light stretched and reddened by billions of years of cosmic expansion, show us the universe as it appeared when it was young, less than 1 billion years old. To observe the cosmos is to witness history, to watch the universe unfolding across time, frame by frame. This concept, called look-back time, transforms every telescope into a time machine. When astronomers study distant galaxies, they are not merely measuring how far away they are, but how long ago their light left them. The universe becomes a vast archive, with light from different epochs constantly arriving, carrying information about stars that formed, galaxies that merged, black holes that fed, all in the ancient past. The farther we look, the younger the universe appears, until we reach the cosmic microwave background, light from when the universe was only 380,000 years old, the oldest light we can see. Yet light's finite speed is not the only curious feature of time in the cosmos. Einstein's theory of relativity revealed something even stranger. Time itself is not absolute. It flows at different rates depending on motion and gravity. This is not an illusion or a trick of perception, but a fundamental property of the universe. Time is relative. Near massive objects, where gravity is strong, time runs slower. A clock placed near the surface of a neutron star ticks more slowly than an identical clock far from any mass. For an observer at a safe distance, watching someone fall toward a black hole, that person appears to move slower and slower as they approach the event horizon, their watch ticking more and more sluggishly until they seem to freeze at the boundary, asymptotically approaching but never quite crossing. Yet for the falling person, time proceeds normally. They cross the horizon in finite time by their own reckoning, unaware of the temporal distortion their motion creates for distant observers. This phenomenon, gravitational time dilation, has been measured with exquisite precision using atomic clocks. A clock placed on a mountaintop runs slightly faster than one at sea level. GPS satellites orbiting Earth experience weaker gravity than clocks on the ground, and their onboard clocks tick faster by about 45 microseconds per day. Without correcting for relativistic effects, GPS navigation would accumulate errors of several kilometers within a single day. The technology we use daily functions only because we account for the malleability of time. Motion also affects time's passage. An astronaut traveling at high speed ages more slowly than someone remaining at rest. This effect, called velocity time dilation, becomes significant only at speeds approaching the speed of light, far beyond current technology. But it has been verified experimentally using particles accelerated to nearly light speed in colliders. Muons, unstable particles that normally decay in microseconds, live much longer when moving at 99.9% of light speed, their internal clocks slowed by their tremendous velocity. These relativistic effects seem exotic, but they remind us that time is not a cosmic metronome ticking uniformly everywhere. It is a dimension interwoven with space, flexible and variable, responding to mass and motion. The universe does not have a single universal clock, but countless local time frames, each flowing at its own rate. For humans, time perception is an entirely different matter, a product of neurology and psychology rather than physics. Our experience of time passing is subjective, shaped by attention, memory, and emotion. Children perceive time as moving slowly. Summers last forever. Years stretch endlessly. Adults often feel time accelerating, each year seeming to pass more quickly than the last. This acceleration is not imaginary. It reflects how our brains process temporal experience. One theory suggests that as we age, each unit of time becomes a smaller fraction of our total life experience. A year to a 5-year-old represents 20% of their entire existence, a substantial period. A year to a 50-year-old is only 2% of their life, a much smaller fraction. Time seems to speed up because each moment occupies a diminishing proportion of our accumulated experience. Attention also warps our time perception. Novel experiences, rich in detail and requiring focus, feel longer in the moment and are remembered as extended periods. Routine, repetitive days blur together, seeming to pass quickly and leaving little trace in memory. This is why childhood, filled with new experiences, seems so long in retrospect, while adult years, often marked by routine, can feel as though they vanish like water through fingers. The brain constructs time perception from sensory input, memory formation, and neural rhythms. It is not a passive clock, but an active interpreter, adjusting its sense of duration based on context. In moments of danger, time seems to slow, not because it actually does, but because the brain encodes memories more densely, creating the illusion of extended duration when recalled. Drugs, meditation, and even body temperature can alter time perception, demonstrating that our experience of time is a mental construct, flexible and subjective. Yet beneath our subjective experience and Einstein's relativistic framework, the universe itself possesses intrinsic rhythms. Pulsars spin hundreds of times per second with regularity so precise they rival atomic clocks. Binary stars orbit each other in periods ranging from hours to millions of years. Galaxies rotate, their spiral arms sweeping through space over hundreds of millions of years. Entire clusters of galaxies orbit their common center of mass over billions of years. These cosmic cycles are the universe's heartbeat, rhythms playing out on scales far beyond human perception. A pulsar's millisecond flashes seem impossibly fast, yet they are perfectly stable. The spinning remnant of a star maintaining its rotation for potentially billions of years. Galactic rotation is so slow that humanity's entire history represents a minuscule fraction of a single galactic year. The Milky Way takes about 225 million years to complete one rotation, meaning the Sun has circled the galactic center only about 20 times since its formation. Even the cosmic microwave background carries a kind of rhythm, the fluctuations imprinted on it reflecting acoustic waves that rippled through the early universe. These sound waves, frozen into the structure of space-time when the universe was 380,000 years old, set the scale for galaxy clustering and large-scale structure. They are the universe's earliest music, a note struck in the primordial plasma and still echoing in the distribution of galaxies today. Time in the cosmos is both more rigid and more fluid than we imagine. Light travels at a fixed speed, creating hard limits on causality and communication. Yet time's flow varies with gravity and motion, bending and stretching according to circumstances. Human perception adds another layer, a subjective experience shaped by biology and consciousness, giving us a personal relationship with time that can feel entirely disconnected from the objective passage of seconds. This interplay between cosmic and human timescales offers a meditation on existence itself. We live such brief lives against the backdrop of a universe billions of years old. Entire civilizations rise and fall in cosmic eye blinks. Yet our subjective experience is all we have, the only window through which we can perceive the universe at all. Our moments feel long or short, based on internal states, even as galaxies wheel overhead in their patient orbits, indifferent to our haste or leisure. There is something calming in recognizing this disconnect, in understanding that the universe operates on timescales so vast that our anxieties and urgencies are contextually minuscule. The stars will continue their slow evolution, whether we hurry or rest. Galaxies will merge billions of years from now, regardless of how we spend our afternoons. This is not to diminish human experience, but to place it in perspective, to recognize that we are part of something vastly larger, playing out across time frames that render our concerns simultaneously insignificant and profoundly meaningful. For in our brief flicker of consciousness, we have learned to measure cosmic time, to understand that the universe has a history stretching back 13.8 billion years, to calculate the ages of stars and predict the future expansion of space. We have discovered that time itself is relative, that it bends and stretches, that our perception of it is a construct of minds attempting to navigate reality. These are extraordinary achievements for creatures whose lives span mere decades. Imagine the nested rhythms of existence. Your heartbeat, roughly once per second. The Earth's rotation, once per day. Its orbit, once per year. The Sun's orbit around the galaxy, once per 225 million years. The collision of the Milky Way and Andromeda, perhaps 4 billion years from now. The gradual cooling of white dwarfs over trillions of years. Each rhythm is valid, each timescale real, from the briefest quantum fluctuation to the longest cosmic epoch. We exist within this nested hierarchy, conscious and aware, experiencing the subjective flow of moments while being part of a universe whose story unfolds across timescales almost beyond imagination. Time, in all its forms, connects everything, linking the immediate to the eternal, the human to the cosmic, reminding us gently that we are both fleeting and part of something timeless. There is a poetry written in your bones, a story older than mountains, older than oceans, older than the earth itself. Every atom in your body, the carbon in your cells, the oxygen in your lungs, the calcium in your skeleton, the iron in your blood, was forged inside a star. You are not merely in the universe. You are made of the universe, assembled from stardust scattered across space by stellar explosions billions of years ago. This connection is not metaphorical, but literal, a cosmic genealogy linking your existence to the most violent and beautiful processes in nature. The story begins in the first moments after the Big Bang, when the universe was unimaginably hot and dense. In those opening minutes, when temperatures exceeded billions of degrees, the simplest atomic nuclei formed through a process called primordial nucleosynthesis. Protons collided and fused, briefly creating deuterium, then helium, with trace amounts of lithium emerging in the cosmic cauldron. But the expansion and cooling happened quickly, too quickly for fusion to proceed beyond these lightest elements. For hundreds of millions of years, the universe contained essentially nothing but hydrogen and helium, with tiny traces of lithium. These were the only elements available, the primordial building blocks from which everything else would eventually be constructed. Yet hydrogen and helium alone cannot make planets or oceans or living creatures. Life as we know it requires heavier elements: carbon, nitrogen, oxygen, phosphorus, sulfur, and many others. These did not exist yet. They had to be created. The creation happened inside stars, in the nuclear furnaces burning at their cores. The first stars, those massive population 3 giants forming from pristine primordial gas, began the work of cosmic alchemy. In their cores, where temperatures reached tens of millions of degrees, hydrogen nuclei fused into helium, releasing the energy that made stars shine. But as these stars aged and their hydrogen fuel depleted, their cores contracted and heated further. reaching the 100 million degrees needed for helium fusion. Helium fusion is elegant and improbable. It requires 3 helium nuclei to collide nearly simultaneously, a process called the triple alpha reaction, because helium nuclei are also called alpha particles. When 3 helium nuclei fuse, they create carbon, the foundational element of organic chemistry, the backbone of every molecule that makes life possible. Without this reaction, without stars reaching the precise conditions needed for helium burning, carbon would not exist, and neither would we. But stars did not stop at carbon. As helium ran low, massive stars contracted their cores again, reaching even higher temperatures. Carbon nuclei began to fuse, creating oxygen, neon, and magnesium. Oxygen fusion followed, producing silicon and sulfur. Each stage required higher temperatures, burned faster, and yielded less energy than the previous one. A star might burn hydrogen for billions of years, helium for hundreds of millions, carbon for thousands, and oxygen for mere months. The process continued through progressively heavier elements, each fusion reaction building nuclei with more protons, climbing the periodic table step by step. Silicon fusion marked the final stage of stellar nucleosynthesis, creating iron, cobalt, and nickel, elements near the peak of nuclear binding energy. Iron is where the process stops. Fusing iron requires energy rather than releasing it. Once a massive star's core turns to iron, fusion ceases and disaster follows swiftly. Without fusion to generate outward pressure, gravity wins. The core collapses catastrophically in less than a second, compressing to nuclear densities. The collapse rebounds in a supernova, an explosion so violent it briefly outshines an entire galaxy. In those moments of unimaginable energy, elements heavier than iron are forged. Rapid neutron capture processes build gold, platinum, uranium, and all the elements beyond iron in the periodic table, creating them in quantities that stellar fusion could never achieve. The explosion does more than create heavy elements, it scatters them. The supernova shockwave tears through the star's outer layers, blasting gas enriched with newly forged elements into the surrounding space at thousands of kilometers per second. This gas, heated to millions of degrees, glows brilliantly as it expands, forming the expanding remnants we observe as supernova remnants, like the Crab Nebula or Cassiopeia A. These explosions seed the galaxy with heavy elements, enriching the interstellar medium. Each generation of stars inherits material from previous generations, growing progressively richer in elements heavier than hydrogen and helium, which astronomers call metals, regardless of whether they are metals in the chemical sense. The first stars were metal-free. The Sun, a relatively recent star by cosmic standards, formed from gas enriched by countless previous stellar cycles, giving it about 2% heavy elements by mass. This enrichment was essential for Earth's formation. When the solar system coalesced from a cloud of gas and dust about 4.6 billion years ago, that cloud contained not just hydrogen and helium, but carbon, oxygen, silicon, iron, and every other element needed to build rocky planets. The dust grains that clumped together to form Earth carried elements synthesized in stars that died billions of years earlier, perhaps hundreds or thousands of light years away. The iron in Earth's core, which generates our protective magnetic field, came from supernovae. The silicon and oxygen in rocks, the calcium in limestone, the carbon in fossil fuels, all were created in stellar cores and scattered by stellar deaths. Without this enrichment, Earth would not exist. There would be no solid surface, no oceans, no atmosphere capable of supporting life. The planet itself is a collection of stardust, aggregated by gravity into a sphere orbiting an ordinary star. Life's connection to stars goes even deeper. The human body contains about 60 different elements from the periodic table, many in trace amounts, but all essential for various biological processes. Carbon forms the backbone of every organic molecule. Proteins, DNA, carbohydrates, lipids. Oxygen, bonded to carbon and hydrogen, makes water, which comprises about 60% of your body weight and is the medium in which biochemistry occurs. Nitrogen, forged in stars through carbon fusion, is essential for amino acids and nucleic acids. Phosphorus, created in supernovae, forms the backbone of DNA and the energy currency of cells, ATP. Sulfur, also from supernovae, appears in crucial amino acids like cysteine and methionine. Calcium, produced in the final stages of massive star evolution, builds bones and teeth and plays vital roles in cellular signaling. Even trace elements carry stellar origins. Iron in hemoglobin, the protein that carries oxygen in blood, allows complex multicellular life by enabling efficient oxygen transport. Magnesium sits at the heart of chlorophyll, making photosynthesis possible. Zinc, copper, manganese, and cobalt serve as cofactors in enzymes, catalyzing reactions essential for metabolism. Every one of these elements was created in stars. The journey from stellar core to living tissue spans billions of years and unimaginable distances. Imagine a massive star exploding 10 billion years ago in a distant region of the galaxy. Its shock wave disperses iron atoms into space, where they drift through the interstellar medium, perhaps ionized by radiation, perhaps locked in dust grains. Over millions of years, these atoms migrate across the galaxy, mixing with gas clouds, until eventually they become part of a molecular cloud collapsing to form new stars. One such atom might find itself in the disk of gas and dust surrounding the young sun, colliding with other particles, sticking to growing planetesimals. Eventually, it becomes part of Earth, perhaps buried in the mantle for billions of years before volcanic activity brings it to the surface. Weathering releases it into soil, where it is absorbed by plants, consumed by animals, and eventually finds its way into your bloodstream, becoming part of a hemoglobin molecule carrying oxygen to your cells. This single iron atom has traveled across light years and eons, from the core of a dying star to the interior of your body. And it is not alone. Every atom in you has a similar history, a cosmic journey connecting your existence to stellar processes billions of years old. You are, quite literally, the universe made conscious, stardust arranged in such a way that it can contemplate its own origins. The realization has profound implications. It means we are not separate from the cosmos, but intimately part of it, products of the same physical processes that create stars and galaxies. The calcium in your bones was once in the heart of a red giant, fused from lighter elements as the star swelled and cooled. The oxygen you breathe was forged in a massive star's core over millions of years. The gold in any jewelry you wear was created in the violent collision of neutron stars, an event that sent gravitational waves rippling through space-time. This connection extends beyond individual elements to the patterns and structures of life itself. The chemistry that makes biology possible operates according to the same quantum mechanical principles that govern fusion in stellar cores. The information encoded in DNA follows the same physical laws as the light-carrying signals across the cosmos. Life is not separate from physics, but an expression of it. Matter and energy organized into self-replicating, evolving systems. Even the environment that nurtures life owes its existence to stars. Earth's atmosphere, once dominated by carbon dioxide and nitrogen, was transformed by photosynthetic organisms, producing oxygen, a waste product that gradually accumulated over billions of years. That oxygen came from water molecules split by sunlight, the hydrogen escaping to space while oxygen remained, creating the breathable air we depend on. The energy driving photosynthesis comes from the sun, whose light originates in fusion reactions converting hydrogen to helium. In this sense, we are solar-powered, sustained by starlight, both directly and through the complex web of life that channels solar energy through ecosystems. Every breath you take, every movement you make, is powered ultimately by fusion happening 93 million miles away in the sun's core. The energy was generated 8 minutes ago in photon time, though the photons themselves were created by fusion reactions in the core and took tens of thousands of years to random walk their way to the surface before streaming into space. The cosmic connection extends to time as well as matter. The atoms in your body are older than Earth itself, forged in stars that lived and died before the solar system formed. You are made of matter, 13.8 billion years old, nearly as ancient as the universe itself. Yet these ancient atoms are arranged in patterns that change constantly. Your body replaces most of its cells over years and decades, atoms cycling in and out, borrowed temporarily from the environment and returned, the pattern persisting even as the constituents change. To understand that we are made of stardust is to feel a connection to the universe that transcends ordinary existence. It dissolves the false boundary between self and cosmos, revealing that we are not isolated beings on an insignificant world, but integral parts of a vast, interconnected process billions of years in the making. The universe took hydrogen and helium, ran them through stellar furnaces for eons, scattered the products across space, gathered them into new stars and planets, and somehow, through chemistry and evolution, produced consciousness capable of understanding its own origins. This is perhaps the most profound realization science offers, that the universe has evolved to the point where it can contemplate itself through us. We are the cosmos waking up, matter organized in such intricate patterns that it becomes aware, looks outward, asks questions, and discovers that it came from stars. Every time you gaze at the night sky, you are looking at your ancestral home, the stellar crucibles that forge the atoms of your being. Imagine the journey those atoms took to become you, from the heart of ancient stars to the cold of interstellar space, from collapsing clouds to planetary surfaces, from soil and water into living cells, and finally into the complex structures of your body. You carry within you the history of the cosmos, a story written in elements, connecting you to supernovae billions of years ago and to every living thing on Earth. All of us assembled from the same stellar ashes, children of the stars, made of light and time and nuclear fire, briefly gathered into forms capable of wonder. For all that we have learned about the universe, for all the equations solved and observations made, the cosmos still guards its secrets jealously. There are mysteries scattered across the heavens like unopened letters, phenomena we can observe but cannot yet explain, questions that pull at the edges of our understanding and remind us how much remains unknown. These mysteries are not failures of science, but invitations, quiet whispers from the universe suggesting there is always more to discover, always another layer of reality waiting to be unveiled. Some mysteries hide in the outer reaches of our own solar system, tantalizingly close, yet frustratingly elusive. Beyond Neptune, in the cold darkness where sunlight is barely a glimmer, there may lurk a planet we have never seen. Astronomers call it Planet 9, a hypothetical world perhaps 10 times the mass of Earth, orbiting the Sun at a distance so vast it takes tens of thousands of years to complete a single revolution. The evidence for Planet 9 is indirect but compelling. Several trans-Neptunian objects, icy bodies, orbiting in the furthest reaches of the solar system, have orbits that cluster in peculiar ways. Their elliptical paths align more than random chance would suggest, tilting in similar directions as though shepherded by the gravity of an unseen giant. Computer simulations show that a distant, massive planet could produce exactly this clustering, its gravity gently tugging on these distant objects over millions of years. Yet despite dedicated searches, Planet 9 remains invisible. If it exists, it is so far away and reflects so little sunlight that even powerful telescopes have not spotted it. The search continues, each survey eliminating portions of the sky where it cannot be, slowly narrowing the possibilities. Perhaps one day soon, a faint point of light will reveal itself in archived images or new observations, and we will discover we have 9 planets after all, the 9th hiding in plain sight at the edge of darkness, a world that has orbited unseen since the solar system's birth. Beyond our solar system, other mysteries drift through the galaxy. Rogue black holes, ejected from their birth clusters or set wandering by galactic interactions, may roam through space at tremendous velocities. These cosmic nomads would be nearly impossible to detect directly, visible only when they pass in front of distant stars, their gravity bending light in telltale patterns, or when they encounter gas clouds, briefly flaring as material spirals inward. Some observations hint at these wanderers. X-ray sources moving through the galaxy with no visible counterpart, gravitational lensing events that cannot be explained by known objects. These may be signatures of runaway black holes traveling at hundreds or thousands of kilometers per second. Imagine a black hole, perhaps 10 times the sun's mass, careening through the galaxy's spiral arms, invisible and silent. A gravitational hazard passing through the night with nothing to mark its presence except the faint distortion of background starlight. The idea is both unsettling and magnificent. These dark travelers threading through the spaces between stars, most destined never to encounter anything substantial, forever falling through the void at velocities that will carry them across the galaxy many times before the stars themselves burn out. They are ghosts in the cosmic machine, remnants of stellar deaths set loose to wander eternally. Closer to the galactic center, another mystery looms large and energetic. Extending above and below the plane of the Milky Way, stretching for tens of thousands of light years, are the Fermi bubbles, enormous lobes of high-energy gamma rays discovered only in 2010, when the Fermi Gamma Ray Space Telescope compiled its all-sky survey. These structures are vast, each bubble encompassing a volume larger than the entire visible disk of our galaxy, glowing with energies that suggest violent processes at work. The bubbles are thought to be the remnants of ancient activity in the galactic center, perhaps an outburst from the supermassive black hole Sagittarius A that lurks there. Millions of years ago, this black hole may have undergone a feeding frenzy, consuming vast amounts of gas and launching powerful jets perpendicular to the galactic plane. These jets would have carved through the surrounding medium, inflating bubbles of hot plasma that continue to glow in gamma rays today. Alternatively, the bubbles might have been inflated by a burst of star formation near the galactic center, countless massive stars forming, living briefly, and exploding as supernova within a relatively short cosmic time frame. The combined energy of these explosions could have driven winds powerful enough to create the observed structures. The truth remains uncertain. The bubbles, a testament to events that unfolded millions of years ago. Their light only now reaching us, carrying information about processes we are still struggling to fully understand. Even more enigmatic are the strange shapes occasionally photographed in deep space, objects and patterns that defy immediate explanation. Perhaps the most famous recent example is the cosmic question mark, a formation captured by the James Webb Space Telescope that resembles, uncannily, the punctuation mark floating in the darkness between galaxies. This structure is likely two galaxies in the process of interacting, their gravitational dance distorting their shapes into this peculiar configuration, a cosmic coincidence that happened to resemble a human symbol. Yet such serendipitous discoveries remind us that the universe contains countless structures and phenomena we have never cataloged, patterns and formations arising from the complex interplay of gravity, gas dynamics, radiation, and time. Each new survey of the sky reveals objects that do not fit neatly into existing categories, challenging astronomers to expand their understanding or develop new theories. Fast radio bursts, millisecond duration pulses of radio waves from distant galaxies, were discovered only in 2007 and remain partially mysterious. Some repeat, others do not. Their origins are still debated, with magnetars, neutron stars with extraordinarily strong magnetic fields, emerging as leading candidates. Yet the diversity of observed properties suggests multiple mechanisms might be at work, different cosmic engines producing similar signals through convergent phenomena. The questions pile up, each answered question spawning new ones. What exactly are gamma ray bursts? And why do they come in two distinct populations with different durations and energies? What causes the extremely high-energy cosmic rays that occasionally strike Earth's atmosphere? Particles with energies far beyond anything human-built accelerators can achieve. Their sources unknown despite decades of study. What are the mysterious, ultra-luminous X-ray sources that shine brighter than any stellar mass black hole should be able to, yet dimmer than the supermassive black holes in galactic centers? Dark matter and dark energy, those two great unknowns dominating the universe's mass and energy budget, remain fundamentally mysterious, despite indirect evidence confirming their existence. We know dark matter is there from its gravitational effects, yet we have never detected a dark matter particle. We know dark energy drives the universe's accelerating expansion, yet we have no deep understanding of what it is or why it has the value it does. These are not minor gaps in knowledge, but chasms, fundamental aspects of reality we observe but cannot explain. The mysteries extend to the very nature of the cosmos itself. Is our universe unique, or is it one among countless others in a vast multiverse? Do the laws of physics we observe here apply everywhere, or might they vary in regions beyond our horizon? Did time truly begin at the Big Bang? Or was there something before, another universe perhaps, that collapsed and rebounded into ours? These questions push against the boundaries of testable science, yet they arise naturally from our current theories and observations. Black holes themselves, though theoretically well understood, still harbor mysteries. What happens at the singularity at their center, where our equations break down and physics as we know it ceases to function? How is information preserved when matter falls into a black hole, satisfying the laws of quantum mechanics which forbid information destruction? The black hole information paradox has occupied theoretical physicists for decades, with proposed solutions ranging from subtle to radical, none yet definitively proven. Even consciousness, the very quality that allows us to ponder these mysteries, remains unexplained by science. We are matter organized in certain ways, neurons firing in patterns, yet somehow this produces subjective experience, the feeling of being, the quality philosophers call qualia. How does the universe, through us, become aware of itself? This question sits at the intersection of neuroscience, philosophy, and perhaps physics, a mystery as profound as any cosmological puzzle. Yet there is beauty in these unknowns, a kind of comfort in recognizing how much we do not understand. The universe is not a solved puzzle, but an ongoing exploration. Each answer revealing new questions, each discovery opening new territories to investigate. The mysteries are not obstacles, but opportunities, invitations to keep looking, keep wondering, keep pushing the boundaries of knowledge. To live in a time of mystery is to live with possibility. Planet 9 might be found next year or never. Dark matter particles might be detected in an underground laboratory next month or remain elusive for generations. Fast radio bursts might be explained by a single elegant theory or reveal themselves as diverse phenomena requiring multiple explanations. We do not know, and that not knowing is itself a gift. These unknowns are not failures, but promises. They assure us that the universe still has stories to tell, secrets to share, wonders to reveal. And perhaps that is the most beautiful mystery of all, that in a cosmos 13.8 billion years old and 93 billion light years wide, containing hundreds of billions of galaxies each with hundreds of billions of stars, we can still be surprised, still encounter phenomena that challenge our understanding, still find reasons to keep asking questions. The universe, in its infinite patience, invites us to keep exploring, one gentle mystery at a time, reminding us that wonder is not a resource to be depleted, but a renewable gift, offered anew with each observation, each discovery, each quiet moment of contemplation beneath the stars. And so we drift to the end of our quiet journey through the cosmos, though in truth, there is no end to what the universe has to offer. We have wandered together from the first fiery moments of the Big Bang through 13.8 billion years of cosmic history, across 93 billion light years of space, touching mysteries both solved and unsolved, contemplating scales that dwarf human experience yet somehow remain comprehensible through the patient work of science. The universe continues its patient work. Galaxies turn slowly through the night. Stars fuse hydrogen in their cores. Light travels across the void, carrying information from distant epochs. None of it requires your attention, yet all of it welcomes your curiosity whenever you choose to wonder. If you have enjoyed this journey through the cosmos and would like to explore more worlds of science and wonder, we would love for you to like, subscribe, and share your thoughts in the comments. But for now, you can allow the story of the universe to fade gently like twilight, leaving only calm behind. If sleep comes, let it carry you softly. If you remain awake, you are welcome to stay, to listen again, or to let the next video continue your voyage into the quiet wonders of existence. Rest well, and remember, you are made of ancient starlight, atoms that have journeyed across billions of years to become you, briefly gathered into a form capable of contemplating infinity. The universe is vast, patient, and beautiful, and you are part of it, now and always. Good night.